Hi everyone, so this is the recording for Class 6, which will be sort of following on from the stuff we did in Class 5, which was introducing basic statistical analysis. In our case, we'll be looking to sort of move on from that and introduce a few more sort of statistics. So in this class, we'll be using the same data sets as usual, so the 7 data sets that we looked at last time, and we'll be introducing one more measure of one more sort of statistic, and that's the auto mutual information. Okay, so you'll need the functions mentioned on the sheet. But the idea of the mutual information, so there is a worksheet, a sheet describing the mutual information on Moodle. So it's a PDF file you can find on there, which you should read in detail and try and get your head around the idea. But the basic idea is that what we want is some sort of measure of dependency. So most correlation is a very well known measure of dependency, but it's only a linear measure. Okay, so correlation only find linear correlation. Okay. So we talked about various examples of things where there's a clear dependency in which the correlation is 0. So for example, if you have a circle, points on a circle, the correlation will be 0, expectation. The logistic map, so from one step to the next in the logistic map, the correlation is exactly 0. So we look for something that tells us about these non-linear relationships that tend to occur in this field, and a good way of doing that is the auto mutual information. So the basic idea of mutual information is that we want to know, we have 2 variables, x and y, and we want to know, if we know x, what extra information do we learn about y? So in other words, what do we know about y prior to knowing x, and what do we know as a result of knowing x, and how much extra information do we gain? So doing this we have no reliance on linear correlation, so we can uncover non-linear relationships just as easy as linear relationships, and so it just gives us a sort of alternative measure to the autocorrelation. Okay, so let's look at some of these data sets and show how the auto mutual information works, and where cases in which it is able to show these relationships where the linear correlation is not. So let's start with a linear data set. So we talked last time about how the gluttony data set is a linear stochastic process. So let's read that in. We'll call it X. We read in the functions as normal, so we need to read in the autocorrelation, and we see what that looks like. So we do autocorrelation of linear time series up to lag 50. Okay, and then we need to plot that. We see what that looks like. So we expect it to the autocorrelation to decline with time, and it's exactly what we see. So we expect that there is some autocorrelation because it's an AR1 process, but the further you go ahead in time, the greater the lag, the smaller that value is, and until eventually it just decays down to 0, so that the memory of the process is lost. So let's see what happens if you, instead of using the autocorrelation, you use the auto mutual information. So again, we read in the file, and then we plot the auto mutual information instead of the autocorrelation. So firstly, we need to read in that there are a couple of functions that the function depends on. So we need to read these in first. So we need the entropy function as well. So now we've done this, we should be able to just plot the auto mutual information as a function of lag. Okay, so so just to be clear, we need to, here we have to choose a certain number of bins. So so if you read the PDF, the number of bins should make sense. But effectively, number of bins is always a trade-off between having a good number of data points in each bin, but also sort of sampling the distributions well. So it's always quite a difficult trade-off. So we can try different numbers of bins. So we start off with 8 and see what happens. Okay, so just calculating that. So here fairly quickly the auto mutual information declines to 0. But if we want to look at this sort of more clearly, we can define define this time series, this vector as A, so we can exclude the first point, so we can look at it in a bit more detail. So we just do 2 to 50, and we see it declines sort of fairly quickly. Note that the mutual information is always greater than 0, so any kind of randomness is going to be in the positive direction. So we always expect it to be greater than 0 in practice, but even if there's no mutual information. So we see here that we have a decline in the same kind of way as the autocorrelation. So that's not surprising. The autocorrelation, the auto mutual information, there's only linear correlation here, so both measures show that up. So let's move on to something a bit more interesting. So we looked at this greed data set. So let's read that in. Oh, sorry, it should be scan. Just so we scan that in. Okay, so again we can plot the autocorrelation. We should be able to go up and find that again without typing it out again. And here, interestingly, here the autocorrelation is 0, effectively 0. So after one lag, after one time step, the linear correlation just shows up no information at all. Okay, so clearly it looks very much like the linear correlation is just 0. So what happens if we do the auto mutual information? We can take a look. Again, we need the number of bins, so we'll try 8 again. So here it makes sense to define this vector f, and then just plot the points from 2 steps onwards, from lag 1 onwards, sorry. So we just plot f 2 to 50, so we can get a better idea about what the auto mutual information looks like. And here, interestingly, we see, so the linear correlation showed up as 0. There was 0 autocorrelation, but actually looking at the auto mutual information, we find that actually, because this is a non-linear stochastic process, we find that actually there is some information. So the auto mutual information tells us that by knowing one point, it tells us something about the following point throughout the time series. Okay, so we show that. So here we see that actually, the linear correlation was useless in this case, but the auto mutual information has shown that this information is here. So there is a sort of dependency between consecutive points. Okay, so if we were trying to work out what the data set is, this is a real clue, because if the linear correlation is 0, or effectively 0, but the auto mutual information is quite a lot different to 0, and it looks stochastic, we look at things like delay plots, it looks stochastic, then this very much suggests that this is a non-linear stochastic process. Okay, so let's move on to another time series. So we can look at anger. So that's so we worked out that anger is real data, and actually it's returns of IBM stock. Okay, so let's plot the time series again, just to remind you what it looks like. So we have this, it looks pretty random. The mean is roughly 0, but we have these sort of big shocks in the share price. So yeah, this is very much real data. So we generally expect there to be 0 correlation in share stock prices, well, in returns from stock, because if there wasn't, then you could people would obviously use that information and buy stock, and it would push the price down. So fundamentally in finance, we expect there to be 0 correlation. So we can plot the autocorrelation and confirm that that's the case. So we'll do that up to lag 50 again. And we do indeed find that to be the case. So we just have this sort of scatter around 0 for lag, for any lag. But what happens if we plot the auto image information? So really, we expect this to be, we expect the same kind of result. We don't really expect to know much about the next point. We don't expect to see much relationship here. So we do it. Again, we want to look a bit closer. So we just define a new vector f, and then we plot f from 2 to 50. So actually, it seems to be a bit scattered. There's a bit of randomness. It seems to be a bit more sort of variability going on here, but maybe there's a little bit of information, but it could just be random. But this is the point. This is how you use the auto mutual information is effectively showing that there's not really much information here at all. In this case, it agrees with the autocorrelation. Okay, so we looked at 3 cases really. The case when we have linear correlation, so autocorrelation and mutual information agree. The case where we have only non-linear dependency, so autocorrelation shows up nothing. The auto mutual information shows that there is dependency. And the third case in which we don't expect to see any sort of relationship, and really there's pretty much agreement on this. Okay, so then the next part of the worksheet asks you to generate a time series of logistic map data with parameter value a equals 4. So and then to plot the mutual information and the correlation up to lag 25. So we're doing the same kind of thing here. So let's do that. So you should still have the logistic function from before. Just remind myself how we run this. So okay, so it's a function of the initial condition. So we'll say 0.4, say value of a, and we'll run it out for 4,096 points. I think that's what. Yeah, so it doesn't ask you how long the time series should be. So okay, so we need to load this in first. We generate time series and call it x. And here we have it. So then we can calculate the autocorrelation x up to lag 25, and if we plot that, we should find by construction that the autocorrelation for any lag is around 0. Taking a little bit of time, but yeah, here we go. Exactly what we find. Now we can plot the auto mutual information, which is 8 bins this time. And actually here, yeah, so here we see that there is a dependency. So we have this 0 linear dependency, but the auto mutual information is able to find this dependency. So remember that there's a huge amount of information. It's not a linear relationship, but this quadratic curve that's defined by the logistic map, there's a huge amount of information. If you know xi, then it tells you a huge amount about xi plus 1. Okay, so that's really the point that we're trying to make there. So finally, so this was a kind of a challenging question, really. So don't worry too much if you were not able to do this one. But the question was just, how do we decide at what lag there ceases to be mutual information? So for autocorrelation, it can be done analytically. You can find a 95% confidence interval for the autocorrelation, and then we can see whether the autocorrelation falls within it or not. For this one, it's a question of how would you do it for this one? Well, actually, there are a number of ways you could do this, but I would suggest that a good way would be simply to mix up the time series. So to create a new time series, randomly sample from that time series, so that you're taking away any kind of neutral, any sort of information. So sample without replacement, and calculate the auto mutual information. Do it again. Keep doing this over and over again. And then this gives you a distribution of what the auto mutual information would look like if there were no dependency in the time series. If you're taking out dependency, working out what kind of levels of auto mutual information you expect if there's no, but just by chance, in a case in which there's no dependency, and then you can find like the 95% level, and then put that as a dotted line on your plot. Okay, so that's just one way of doing that. So yeah. So if there are any questions on this, just don't hesitate to ask me. And yeah, and that's the end of that class. Okay, thank you.